Richard Feynman never approached gravity the way most people do. When gravity comes up in everyday conversation, it's usually framed as a simple force. Earth pulls you down, the moon pulls the tides, the sun pulls the planets. It feels intuitive, almost obvious, as if gravity were just another invisible rope tugging on everything with mass. But Feynman loved pointing out that this comfortable picture is exactly where our understanding starts to go wrong. Gravity, he argued, is not wrong because it's mysterious. It's wrong because we think we understand it when we actually don't. What everyone gets wrong about gravity is not a single mistake, but a whole stack of assumptions layered on top of one another, inherited from everyday experience, half-remembered school lessons, and misleading analogies. Feynman's genius was to peel those layers away and show that gravity is far stranger, deeper, and more unsettling than the simple idea of a pull. Feynman often began by attacking the word force itself. When you say gravity is a force, it sounds explanatory, but it isn't. Saying that objects fall because gravity pulls them is, in Feynman's words, like saying opium makes people sleep because it has a dormitive virtue. You've renamed the phenomenon, not explained it. Why should mass attract mass at all? Why does this attraction follow an inverse square law? Why does it act instantly in Newton's formulation, across empty space, without any visible connection? These questions are usually brushed aside in textbooks because the equations work. But Feynman insisted that working equations are not the same thing as understanding. Gravity, he said, is a description, not an explanation. We know how to calculate its effects with astonishing precision, yet we don't truly know why it exists in the first place. One of the biggest misconceptions Feynman addressed is the idea that gravity is somehow weaker or less fundamental than other forces. People often hear that gravity is the weakest force in nature and conclude that it's almost trivial. Feynman flipped this perspective on its head. Gravity appears weak, not because it's not important, but because it adds up. Every atom in your body is being pulled by every atom in the earth. The reason you feel a steady, gentle weight instead of a violent yank is that gravity acts universally and smoothly. Unlike electromagnetism, which can cancel out positive and negative charges, gravity only attracts. There is no negative mass to balance things out. This universality, Feynman emphasized, is what makes gravity so special and so puzzling. Another thing everyone gets wrong about gravity is motion itself. When you drop an object, it feels like gravity causes it to move downward. But Feynman loved reminding students that motion depends on the frame of reference. From the object's own point of view, something very strange is happening. According to Einstein's insight, which Feynman deeply admired, a freely falling object is not being forced at all. It is moving naturally through space-time. The ground rushes up to meet it. This idea sounds absurd at first because it clashes violently with everyday experience, but Feynman delighted in that clash. He argued that the discomfort is a sign you're finally touching the truth. Feynman often used elevators as a way to break people's intuition. Imagine you're inside a sealed elevator. If it's sitting on Earth, you feel your weight pressing on the floor. If the elevator is far out in space and accelerating upward at exactly the same rate, you feel the same weight. There is no experiment you can do inside the elevator to tell the difference. From this, Feynman explained, gravity is not just a force pulling downward, it is indistinguishable from acceleration. What everyone gets wrong is assuming gravity is something out there acting on objects, rather than something deeply tied to the geometry of motion itself. This leads to one of Feynman's most profound points. Gravity is not really a force in the Newtonian sense at all. In Einstein's general relativity, gravity is the curvature of space-time. Massive objects tell space-time how to curve, and curved space-time tells objects how to move. Feynman emphasized that this is not a metaphor. It's not as if space-time is like a rubber sheet. It actually is geometry. When planets orbit the sun, they are not being yanked sideways by an invisible force. They are following the straightest possible paths into curved space-time.
The reason this is so hard to grasp, Feynman said, is that our brains evolved to throw rocks and dodge predators, not to visualize four-dimensional geometry. People also get gravity wrong by thinking it's fully understood just because Einstein explained it better than Newton. Feynman was very clear that general relativity is an extraordinary theory, but it is not the final word. In fact, gravity is the odd one out among the fundamental interactions. We have quantum theories for electromagnetism and the nuclear forces, but gravity stubbornly resists quantization. When Feynman tried to treat gravity like other quantum fields, the calculations exploded into infinities. This wasn't just a technical nuisance, it was a deep sign that something about gravity doesn't fit neatly into our existing frameworks. What everyone gets wrong is assuming because Einstein solved the problem, the mystery is over. Feynman insisted the mystery is still very much alive. Another common misunderstanding is about weightlessness. People often say astronauts are weightless because there is no gravity in space. Feynman loved demolishing this idea. Gravity in low Earth orbit is only slightly weaker than it is on the surface. Astronauts float because they are in continuous freefall around the Earth. They are falling toward the planet, but missing it because of their sideways motion. This simple fact reveals how misleading our everyday language can be. Gravity doesn't disappear, the experience of weight does. Confusing the two leads to endless misconceptions. Feynman also warned against the temptation to turn gravity into something mystical, because gravity acts across empty space and shapes the entire universe. People often imbue it with almost magical qualities. Feynman rejected this entirely. Gravity is not magic, destiny, or cosmic intention. It is a pattern in nature that we describe with mathematics. Those equations are astonishingly accurate, but they are not stories about purpose or meaning. What everyone gets wrong, he argued, is thinking that mystery implies mysticism. For Feynman, the mystery of gravity was beautiful precisely because it was honest, because it admitted the limits of what we know. A subtle misconception Feynman addressed is the idea that gravity is simple. The inverse square law looks elegant and clean, so people assume the underlying phenomenon must be simple too. But simplicity in equations doesn't guarantee simplicity in reality. The deeper physicists dug into gravity, the more complex it became. Black holes, gravitational waves, singularities, these are not fringe curiosities, but direct consequences of Einstein's equations. Feynman pointed out that nature is under no obligation to match our intuition. Gravity only seems simple because we've lived with it all our lives. Feynman was especially critical of explanations that stopped too early. If you ask why objects fall, someone might say because of gravity. If you ask why gravity exists, they might say because mass attracts mass. Feynman saw this as intellectual laziness, not stupidity. Humans crave closure. We like answers that feel final, but science, Feynman argued, progresses by refusing to be satisfied with such answers. Gravity, he said, is not a dull chapter to be endured. It is a profound challenge to human understanding. By smoothing over the conceptual difficulties, education robs students of the chance to experience genuine curiosity. Gravity should make you uncomfortable, he said, because it exposes the limits of what we know. In discussing gravity, Feynman often circled back to humility. Physics is powerful, but it is not omniscient. We can predict eclipses centuries in advance and detect ripples in space-time from colliding black holes billions of light years away. Yet we cannot answer the simplest question of all: why does gravity exist? What everyone gets wrong is thinking that science's success eliminates mystery. In reality, it sharpens it. Feynman's perspective on gravity ultimately wasn't about providing a better explanation. It was about cultivating a better attitude. He wanted people to be comfortable saying, "We don't know," not as a failure, but as an invitation. Gravity, in his view, is a reminder that the universe is deeper than our stories about it. The equations are maps, not the territory. They tell us how gravity behaves, not what it is. When you stand on the ground and feel your weight, it feels like the most ordinary sensation imaginable. Feynman urged us to pause there, to feel the strangeness hidden inside that familiarity. Every atom in your body is tracing a path through curved space-time shaped by the mass of the Earth. Time itself is flowing slightly slower at your feet than at your head. None of this is visible to your senses, yet it is there.